Good afternoon, guys. I hope you're doing well. Um, Sorry, getting a little bit of feedback, hoping I can alleviate that. I apologize. We're going to go ahead and start talking about atoms and atomic structure. So in order for us to move forward talking about chemistry and all the things that we do, we need to be able to talk about how the atom is structured, because that's what determines pretty much everything we do in chemistry. So let's make sure that we understand the concepts of what we're talking. And I'm going to go ahead and share my screen. And I'm going to share that whole screen over there, because there are going to be things that I do over here that I want you to be able to see. First thing we're going to talk about is our topics. Obviously, these are the things that these slides are talking about, the slides that they're on, and the sections in the textbook that they cover. This particular slide is presented entirely for you so that we know that what we're talking about. And so upon review, you know where to go and find things. Now, the first thing I do in each of my lectures is to go through a practice from the last time. So let's go ahead and do that. And since I'm going to do that, I'm not going to go ahead and put it in presentation mode yet. When I do this, I always do it using a handy little tool that I've got. And you'll see that looks like... when I get it to work. That looks like this. So this is effectively a piece of paper that I can draw on. I'm going to use this to show you how I solve these problems. All right, so that's the goal in doing that. In order to do that, I need to be able to see some of the stuff that I have on this. So the practice that we want to do, we want to talk about calculating the mass in grams of 2 cubic inches of gold. So we're going to be talking about 2 cubic inches of gold. I'm told that the density of that gold is 19.3 grams per centimeter cubed, and that 1 inch equals 2.54 centimeters. Okay, I don't know what I'm going to do with that yet, but I'm going to have to do something with it. So I'm going to go ahead and put this right here for now. I'm going to pull up my calculator, because that's the other thing that I typically need when I do calculations. And this is nothing but an electronic version of my calculator so that you can see what I'm doing. Let's talk about how we would do this when we want to talk about going from here to grams. So the first thing I know is that I have 2 inches cubed. All right, I want to convert that to grams. I know that if I can get it to grams, to centimeters cubed, then I can convert it using the density, right? Because this density that I've been given is in grams per centimeter cubed. So if I can take this inches and get it to centimeters cubed, I can use this density. I know that 1 inch is 2.54 centimeters, so I should be able to do that calculation. Now, I'm setting up this, excuse me, this math, 2 inches cubed. Awesome, I know that's what I have. I know that 1 inch is 2.54 centimeters, because that's what they tell me right here. So I put the inches on the bottom, the 2.54 centimeters on the top. I know that's not exactly going to work, because I'm going to have to cube the whole thing. That's going to apply the cube to the 2.54 centimeters, and is going to apply it to the inch, okay? I'm also then, once I have centimeters cubed, because that's what I'll be left with, then I need to use this density, which is 19.3 grams per centimeter cubed. Now I could multiply 19.3 times this whole thing. Would that work? Actually, yes, it will. Now what am I looking at? 19.3 grams per centimeters cubed. What I need to have happen is that this centimeters cubed that I just created needs to go away and leave me with grams. So I need to have the 19.3 grams on the top and the centimeters on the bottom. So that's what I need to do, is multiply 2 times 2.54 times 19.3. 2 times 2.54 cubed times 19.3. All right. That doesn't look right, does it? No, it doesn't. So let's take a step back. I'm going to cube my 2.54. Then I'm going to multiply that by 2. And then I'm going to multiply that now by 19.3. That looks better. I could have done it as 2 times 2.54 cubed. And then times 19.3. And that gives me that same number. The problem that I had was that I had put the 19.3 times 3 as the power. And that's not what I wanted to do. So 6.32540674 blah, 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 blah. It's a big number. Yes. I have how many significant digits? Interesting. This number that they gave me is 1 sig fig. This number that they gave me is a conversion factor and therefore is infinitely significant. So I'm limited to 1 sig fig in my answer. So how the heck am I going to write this as 1 sig fig? Well, the thing that I do is I put this in scientific notation. 6 times 10 to the 2 grams. And that gives me the answer that I need. Okay? Does that make sense to you guys? All right, I hope that does. And of course, if you're not confident in doing that, you can always do the mode, move it to scientific, hit enter, quit that, multiply by 1. And that gives me 6.32 times 10 to the 2. And I know that since it's 1 sig fig, I'm going to leave it as 6 times 10 to the 2. Okay? So there's that. I'm going to move this away so that I can talk about my PowerPoints again, because that's kind of the point. So let's talk about the PowerPoints. And I'm going to put this in slideshow mode now so that we can deal with it from here. Okay? Hopefully there are no questions about that. If there are, remember, please try and give me the lecture that you're talking about, what I was talking about, why you're confused, yada, yada, yada. And that should help me to answer whatever questions you have. You can present that to me via email in my office or over the phone. Over the phone's complicated, but we'll try. Okay. All right. Atomic theory of matter. Elements are composed of extremely small particles called atoms. Hopefully you've heard this before. So everything is composed of atoms. And we used to think that atoms were the smallest things that existed. It's not true. We know that atoms actually have subatomic components. All right. We know that that a particular element is comprised of atoms that are roughly exactly the same. So they should have the same size, roughly the same mass, and the same chemical properties. Atoms of one element are different from atoms of another element. Okay. So it's that structure that determines what we're talking about. Compounds are composed of atoms of one or more elements. Okay, it could be that there are 2 of the same element in it, such as oxygen, which is diatomic, so that's a compound, or it could be something like CO2, where they're different. All right, the same types of atoms are present in the same number for the same compound. All right, we can rearrange atoms in chemical reactions, but we cannot create or destroy them. That is not something that we can do. If we do create or destroy them, then we're doing nuclear chemistry, not chemistry. Okay. One other thing we're going to have to talk about is an atomic mass unit, which is an AMU. All right, I will define that for you in a bit, but I'm going to start using that frame or throwing that term around to talk about some of the things, the subatomic particles. All right. So let's talk about the structure of the atom. Initially, this is what we thought it looked like. Now, this was what we were presented from Niels Bohr. He gave us this particular image. We know that it's no longer true, but it's something that we can use to begin to see how this works. There's a guy named Thomson who discovered that there were very small negatively charged particles in the atom. He called those electrons. They are distributed throughout the atom. We also have something discovered by Rutherford called protons. Those are positive in charge. They have the same number of protons as there are the number of electrons. So an atom should be neutral, okay, electrically neutral. If that's the case, we have to have the same number of protons as electrons so that our charge is neutral. Those protons are centrally located in the atom, and they contain approximately half the mass of the atom. Okay, we'll talk about that again in just a minute. We also know that these atoms contain neutrons. All right, neutrons have no charge. They are neutral, and they exist in the nucleus of this particular atom. Okay, we also know that that's approximately half the mass. So what are things that I expect you to know from this? You should be able to draw me one of these basic pictures. You should be able to label that there are neutrons, protons, and electrons. Show me where they are. You should be able to tell me that there are the same number of protons and electrons. And for a particular isotope, which we'll get back to, you should be able to tell me how many neutrons are in that too. Okay. Notice that this is a carbon atom. Carbon contains 6 protons and 6 neutrons. Okay. Also has 6 electrons. And that's because it's atomic number 6. We'll get back to that in just a moment. But that's what we're looking at there. When we talk about these atomic particles, we talk about proton, neutron, electron. Again, a proton is positive charge, neutron is no charge, neutral, and electrons, E- or negative charge. The mass in AMUs for these things, for a proton is 1.0073, for a neutron is 1.0087, and for an electron is small, very, very, very small. Okay, so we typically don't talk about electrons when we talk about the mass of the atoms. Another chart for this, we have the same information, proton, positive, it's symbolized as a plus, and the atomic mass unit is 1.0073. Now, the number of protons is equal to the atomic number. The number of electrons has to equal the number of protons in a neutral atom. We'll talk about things that are not neutral atoms in a few minutes. All right. And the number of neutrons determines which isotope we're talking about. Again, we'll talk about those in a few minutes. Now, I wanted to show you some of the information that exists on a periodic table. We'll talk about the periodic table in much more detail in a few chapters, but information that you may be used to seeing if you've seen a periodic table before. So N is the atomic symbol. Here we're talking about nitrogen. I know N is nitrogen because it says that the atomic name is nitrogen. So symbol, name. We have an atomic mass, 14.007. Okay, I have an atomic number, which is 7. I have that this is a gas. That's the physical state of this particular thing. I can see that this thing, this 2s2, 2p3, is an electron configuration. Don't worry about that yet. You'll get to it eventually. But these are some of the things that you may see on different periodic tables. Not all periodic tables contain the same information. If you've looked at the materials that you'll get for the test, the periodic table that you have will have three main pieces of information. The symbol, the atomic number goes with that, the atomic mass, and the name. Okay, so I don't expect you to memorize the symbols and then to be able to give me the names. I don't expect you to know the names and then be able to give me the symbols. That's not how this works. I will give you the atomic number, the mass, the atomic symbol, and the name. Okay, so that's that portion. Now, atomic mass unit. I said I'd define it, so let's define it. Atomic mass unit is a mass exactly equal to 1/12 of the mass of one carbon-12 atom. Okay, carbon-12. Carbon is a C. Its atomic number is 6, and it's listed as a carbon-12. Okay. Carbon-12 is one molecule of the isotope of carbon that contains 6 electrons, 6 protons because it's carbon, 6 electrons because it's neutral, and 6 neutrons. So this number is the sum of the protons and neutrons. That's how I know it's 6 neutrons. So that's the standard unit for measure for talking about atomic mass, is atomic mass units. Okay. Then we can talk about isotopes. What the heck is an isotope? We just talked about one of them, and that was carbon-12. But the thing that matters with isotopes, we know the number of protons is given by knowing the symbol, number of protons, those go together. So that's the number of protons. If I know the number of protons in a neutral atom, I know the number of electrons. The number of neutrons is dependent on which isotope that I'm talking about. Now, typically we find that the number of neutrons is approximately equal to the number of protons, except as we get more massive, things have to get bigger. So that happens. But what we're seeing here is something that I like to term the isotope symbol. So I have a mass number, an atomic number, and an atomic symbol. Remember, atomic symbol goes with atomic number. So those two you're going to get from the periodic table or something that they've told you, something like that. And then you'll see this mass number. Now that mass number is the sum of the protons and the neutrons. Okay, since they're both approximately 1, this mass indicates to me that I have 11 AMUs of mass, 6 of which come from protons. That means the other 5 have to come from the neutrons. Okay, and we can do that kind of analysis for each of these. We'll have 5 neutrons here, 6 here, 7 here, and 8 here. So 11 minus 6 is 5, 12 minus 6 is 6, 13 minus 6 is 7, and 14 minus 6 is 8. So that's how we know how many neutrons are in each of those isotopes. Okay, so an isotope is something that differs only in the number of neutrons that it has. So we find the atomic mass of an isotope by knowing the number of protons and the number of neutrons, adding them together, and getting an isotopic mass. That applies to that one isotope, right? Just that isotope. Isotopic mass is given in the far right column for the number on the top of the symbol of the element, We can find those. And the only way that you'll know them on a particular test is if you're given an isotopic mass and asked to find it, or if you're given the number of neutrons and then asked to provide the isotopic mass. Okay? So that's an isotopic mass. What's an atomic mass? That's the atom one that we talked about. So that's the mass of one particular atom. What else do we talk about? Well, the periodic table has something called a molecular mass, right? The atomic mass is the sum of the protons and the neutrons. In nature, we don't have simply one version of that. So if I'm going to talk about more than one particular atom, I have groups of them, then I have to be able to do that. Now, one of the ways that we talk about these things, the way that we talk about groups of atoms, is to talk about them in terms of moles. So the same way that we have a dozen is 12. A mole represents 6.022 times 10 to the 23rd particles. Okay. When we talk about the mass of that mole, that's an atomic mass. Okay. Because that number of particles is never just one isotope, it's related to how often those isotopes occur in nature. It's never going to be an even number. And that's why you don't see an even number on the periodic table. I don't expect you to know how to calculate what that is, but I expect you to understand what that means, i.e. that there's more than one isotope that exists in nature, and that's what you're looking at, okay? So you need to be able to explain that. So when we do the mass of an atom, we ignore the electrons, we add the number of neutrons, we add the number of protons, and that gives us the mass of that particular isotope. Normally, we would then need to multiply by the proportion that exists and sum the masses. Now, this is how the atomic mass on your periodic table is arrived at. Again, I do not expect you to do this, but that's how we arrive at that number, okay? All right, we talked about atoms. Go atoms. Yay, atoms. Now let's talk about something else. Let's talk about ions. What the heck is an ion? Now, an atom is the smallest unit of a discernible material that we cannot break down without chemical changes. So oxygen always exists as O2 in its elemental form. It can't just be an O by itself. It has to be with something else, and we'll talk about why later, all right? But it exists as O2. So we talk about the elemental form of oxygen as being O2. Carbon is just carbon. Nitrogen is actually one of these diatomic gases as well. So we talk about having single atoms or elemental units of these things. That's great. Those are all neutral. when we talk about ions, all right, you may have heard this term ions. It's because we've changed the number of electrons that exist. So remember we talked about the number of protons and the number of electrons being equal to each other if they were neutral. Well, when they're not neutral, we call it an ion. The reasons for becoming an ion and what that means, we will talk about in detail later. But for now, we're just going to talk about where we show that and what it means. So you'll see that this is Cl minus, this is O2 minus, and Fe3 plus. Those always appear on the right-hand side at the top. So the isotopic mass goes on the left-hand side at the top, number of protons goes on the bottom on the left, and the charge goes on the top at the right. Okay, so that's where we put the charge. When we talk about this Cl minus, we're talking about chlorine having an additional electron. Electrons are negative, so if I add one more, that becomes negative. O2 minus, I've added 2 electrons to that, and Fe3 plus, I've lost 3. Okay, so that's what we're talking about when we talk about ions. So they're no longer equal protons and neutrons. All right. So let's determine the number of electrons that we have when we talk about certain ions. All right, let's talk about this. Now, what I'm going to do is I'm going to back out of this presentation and I'm going to pull up a periodic table for you because I want to be able to do that when we talk about this. Yes, I did just Google periodic table to be able to talk about this. So when we talk about chlorine, all right, we're talking about chlorine. Where exactly am I going to find chlorine? Well, chlorine is over here. He's number 7. Chlorine is 17. All right, so 17 gives me Cl. That means I have 17 protons. Cl minus, having an additional electron, means that I have 18 electrons for chlorine. H plus, H is over here, hydrogen, number 1. H plus means that I am deficient 1 electron. So even though hydrogen should have 1 proton and 1 electron, it's missing 1. It has 1 proton and nothing else. Okay. We talk about phosphorus, P. Phosphorus is P. It's number 15, so I should have 15 protons and 15 electrons. Since there's no charge, that's exactly what I have. We can talk about O2 minus. O is 8, should have 18 protons and 18 electrons, or sorry, 8 electrons. But since I've added 2 electrons to be 2 negative, I now have 8 protons, 10 electrons. Ca2 plus. Ca is over here. He's number 20. He's 2 plus, so he's lost 2 electrons. So instead of having 20 protons, 20 electrons, he has 20 protons and 18 electrons. Mg, when we talk about Mg, he's right here. He's number 12. Okay, Mg being neutral, he has 12 electrons and 12 protons. Okay, Fe3 plus, Fe is right here being number 26. So we have 26 protons. He's 3 plus, he's lost 3 electrons. So he has 23 electrons. N3 minus, N is number 7. So he should have 7 protons, 7 electrons. He's gained 3 electrons. So I have 7 protons and 10 electrons. Carbon is number 6. Be given that he's neutral, he has 6 protons and 6 electrons. Okay, so you should be able to tell me how many protons, how many electrons on a particularly charged molecule. Okay, so based on the ionic charge, you should be able to tell me that. Eventually, we'll get to a point where you can tell me what the charge should be, but we aren't there yet. Okay. Okay. This big again and present again. Yay. All right, next thing we're going to talk about. Molecule. What's a molecule? Yay, what are molecules? Well, all right. So we're going to throw around a term that you don't know. Molecules are made from non-metal materials bonded to other non-metals. If you don't know what that means, don't worry about it yet. All right, I will show you on the periodic table where we're talking about the non-metals. Sorry, I lost my periodic table. when we talk about nonmetals, we're talking about this portion of the table over here. Don't worry about it yet. We'll talk about it again later, but that's what I'm talking about. All right. So when those kinds of things are bound together, that's a molecule and a molecular substance. Okay. So they can be the same thing, such as an oxygen, or have the same element bound to itself, or they can be different things, as in CO or CO2. Then I have two different elements that I'm talking about there. That's a molecule, that's a molecular compound. We use the atomic symbols and subscripts to convey the proportion of that compound. So O2, that means I have two oxygen atoms bound to each other. CO means I have one carbon and one oxygen bound to each other. Okay, and again, we'll talk about the binding later. All right, molecular formulas are those that represent exactly how many of each atom are in the formula. For instance, H2O2. I know that I have two hydrogens, two oxygens. That's exactly how many I have. Okay, that's a molecular formula. But there's this other thing that we talk about. It's called an empirical formula. All right, that's the smallest whole number ratio of the atoms in the formula. So for instance, if we're talking about H2O2, its empirical formula would be HO. So we divide both of them by 2, and that gives me HO. All right, so that's an empirical formula. Now, those are all terms that we're going to need to be able to get to the next part. None of those may make complete sense at this point, and that's okay. They will make sense when they need to make sense. But you need to understand that these are terms we're going to start dealing with. It's going to feel like we're doing a lot of terminology in the very beginning. That's true. This first test will all be terminology, conversions that have nothing to do with chemistry per se. That's all of that stuff. We're not going to really get to the quote-unquote chemistry until after the first test. Once we do, we'll need all of the stuff that we're talking about now to be able to do that. Now, again, I hope that this brings you to a place where you have no questions, comments, problems. But if you have them, please let me know in some way. Again, if you can tell me which lecture we're talking about, sort of kind of what I was talking about and what your question is, that's helpful to me, but we will deal with it as best we can, okay? I hope that takes care of everything for that particular subject. I'm going to stop sharing now, and I hope you guys have a good day, and I'll talk to you soon. Bye.